Hello everyone, this is video 2, Unit 3, Chemistry 1050. I'm going to continue on with these few examples I left you with to try. So let's just do perhaps, I'm just going to say there's maybe we'll do 2 of them here. Let's look at this first example. We've got silver nitrate reacting with copper, making copper nitrate plus silver. So we're going to do a tally to start. Looking on the left-hand side, I will say that one of the helpful hints I want to share with you, which I did not actually write in the PowerPoint yet, is that it typically is easier if you leave hydrogen and oxygen balancing until the end, meaning balance all other elements first. So let's start with silver, for example. Look at how many silvers you have on each side of the arrow. So on the left-hand side of the arrow, meaning on the reactant side, we have 1 silver. On the right-hand side of the arrow, the product side, we have 1 silver. That's good. On the left-hand side in the reactants, we have 1 NO3, 1 nitrate package. It's a polyatomic ion there. And over here, we have 2. That subscript of 2 means there are 2 of those. So I need to put a 2 here. And that is so I can balance that. That means I now have 2 silvers and 2 nitrates, which means I need to put a 2 here. So those are called the coefficients, and now I've balanced the reaction. I've balanced the equation. The equation is actually how I write what is taking place, the reaction in the beaker, in the test tube, or wherever it's happening. Now I'm going to go down and look for one that has hydrogen and oxygen, so I'm going to skip on down here to water, reacting with sodium. So 1 sodium, 1 sodium. 2 hydrogens on the left. 2 plus 1 makes 3 on the right. 1 oxygen on the right, 1 oxygen on the left. So I'm going to leave the hydrogen and oxygen balancing until the end. However, I've started with sodium and there's nothing that needs to happen with sodium. We've got 1 sodium on each side. A little tip. When you're trying to do a situation where you're trying to balance, you've got 2 hydrogens here, and over here you've got 2 plus 1 makes 3. Take the odd number, so 1 is the odd number, not 2 hydrogens, but 1. Double the odd number. It tends to make it more expedient to finish after that. So notice what I had 1 hydrogen here, 1 oxygen. I've doubled it. 1 sodium. So now I have 2 sodiums, 2 oxygens, and 2 hydrogens right there. So I now need to go over and put a 2 here in front of this sodium. I have 2 oxygens, I have 1 oxygen. So that means I need to put a 2 here. This is getting to be a little bit of work. So I had the 2 oxygens, and so I had 2 hydrogens and 2 hydrogens now, which makes 4. I have 2 times 2, I have 4 hydrogens here and 2 oxygens here. So that 2 times 2, you multiply that, that's 4 hydrogens, and there are 2 hydrogens here and 2 here, which make 4. And then we have the 2 oxygens and 2 oxygens. So that one is complete. And then 2 sodium and 2 sodium, just to double check my work. So if you need some more practice, give the other 3 a try. So now we're going to move on to what are called types of chemical reactions. We know what a chemical reaction is, we know what kind of evidence we'd look for, we know how to write the equation that describes the reaction, we know how to balance it. Now we're moving into what are the different types, because not all reactions are the same. We're going to look at these 4 main types in this video, and then in later videos we're going to look at a few other types. But starting with synthesis or combination, which means think of this as element or compound. A and B can represent an element or a compound. So we could have 2 elements, 2 compounds, or 1 of each. A plus B make AB. Notice that decomposition is the opposite. So if you make, decomposition is breaking, undoing it, if you will. Notice how these 2 are complete opposites. And then the single displacement, if we were to use a general A plus BC, notice that A has taken the place of B and B has been displaced. So sometimes this is called single displacement or single replacement. They mean the same thing. And this will be when we have an element plus a compound, and we have, typically it is a metal displacing a metal in a compound, but it also could be a non-metal displacing a non-metal. We'll look at the different types. In a double displacement reaction, A, B, and C, D means we have a metal, non-metal, so we have a compound and another compound. And what happens is the 2 positive ions switch places. So I'm going to go through each of those using some diagrams. So in a synthesis, or what's called a combination, also sometimes called addition, it all has to do with two different elements or two different compounds coming together to recreate one larger one. Typically it's two elements, but there are some exceptions to that. So think of this as A plus B makes AB. So here is an example of how sodium metal reacts with chlorine gas, to make NaCl. And that is the end product right here. So we've got sodium, and then the chlorine gas is infused in, and the two react to make that. In a decomposition, we've got the opposite. So water can be split into hydrogen and oxygen, for example. So this is an example of a decomposition. In the former video, I was talking about how energy is required for reactions. Water certainly is a compound, and there are bonds between those atoms. They're tightly bonded, they're reasonably strong, so some sort of energy must be used, and in this case it's an electrical current to split water into hydrogen and oxygen gas. And so notice the general formula, which I'm doing for each of the different types. So AB breaks into A plus B. In a single replacement reaction, the difference here is we have to compare the two the element on its own, whether it's a metal or a non-metal, so it could be a halogen, in this case it's a metal. Is zinc metal strong enough, meaning reactive enough, more reactive than copper 2? This is a copper 2, it's a transition metal, and I know that because chlorine is -1, and if I have two -1s here, two chloride atoms, this copper must be +2 because there's only one of the copper ions. Is the zinc metal more reactive than the copper metal ion? And so I go to page 154 here in my OER textbook, in that online textbook, and I look to see where is zinc. If zinc is above copper in what's called the activity series of metals, then zinc will replace copper in the compound right here. But if zinc was below, the reaction would not occur. And when you do look on page 154, you'll see that zinc is in fact higher. And so zinc displaces, so you can call it a single replacement or single displacement. They're used interchangeably. The zinc is more reactive. Copper gets displaced and comes out on its own. So copper ends up being the element on its own. So now it's copper solid, and zinc is now the zinc ion. And let's have a look at what that looks like. Here's a nice image from a Pearson chemistry and electronic textbook that I have permission to use, as long as I reference it, of course. So this is what you just saw in this form right here. If zinc metal is placed in a copper 2 chloride solution, what happens? So zinc is sort of a gray color, dull gray color. Here's copper 2 chloride solution. The chlorine would be the green, likely the green image here, the green chloride ions floating around, and then the brown would refer to, I should say, the copper ions floating around, copper 2+. And so what happens here is you see how a copper, that coppery brown rusty copper, sort of it's a reddish brown color, if you will, like think of an old-fashioned copper penny that we no longer have. A copper solid is formed on top of the zinc because the zinc is coming out of the solid form and displacing. Notice how that the brown, let's just call it copper colored, copper ions are actually going out of solution, forming a solid layer on top of the zinc, while the zinc is actually coming out of solid into its these gray ions here. It's coming into the solution and forming zinc chloride solution. So the gray zinc ions are combining with the chloride ions. And so here's a nice diagram that shows what's happening right here. So that, to me, that's a really neat part, is to see that actual copper. And we would see this in the lab, see that residue, that layer form. In a double displacement or double replacement reaction, we also have to consider, will the reaction happen? So we're not using that activity series chart. we're using on table on page 157, we're looking at table 4.1 for what are called solubility rules. And in this particular situation, if we have an aqueous solution of AB and an aqueous solution of CD, and we form two new solutions of AD and CB, meaning they're all aqueous, so they all dissolve, there will be no reaction. In order for there to be a reaction, we actually need to be able to see, let's go way back here to the middle, to the beginning, we need to be able to see that in fact, that if a precipitate forms, see a solid residue, we've actually made something new that is different than what it was before. And that's the only way we would know that there's evidence, is by having what's called a solid formed. And then the only way to have a solid formed is to have something called a precipitate form. So when you look on page 157, you will see that there are rules, and never to be memorized, by the way, rules that say that describe what compounds generally dissolve in water. So meaning they're soluble, and we would write it aqueous behind them. So here's one where we have hydrochloric acid reacting with sodium hydroxide. If NaCl aqueous is formed, then that will be soluble. But now this is not solid, but it's a pure liquid, which is different than aqueous. So we say that we have a product that is not aqueous that is formed, so we say there will be a reaction. I encourage you to have a look at the examples on page 158 and 159, where you are asked to write equations and to finish reactions, and use that table on 157 and look up the subscripts. Look up right here and right here. If they're both aqueous, a reaction will not occur. If one of them is not aqueous, meaning it's liquid or solid, or in those two scenarios, we will say that there is a reaction. So here's a summary of the different types. I briefly went through synthesis, also known as combination or addition, decomposition, which is the opposite, and then the single displacement, also known as single replacement, and then the double. And these two follow rules. This one, we need to follow the activity series to see whether or not a single replacement will happen. And in this type, we have to follow the solubility rules. In the next video, I am going to jump on over here and look at precipitation reactions, combustion, oxidation, reduction, and acid-base. So thanks for watching. Any questions, please post them in the Q&A.